Another problem where dynamic programming is applicable is the matrix chain multiplication problem. Now, before we understand the details of this problem, let's quickly revisit the dot product or matrix multiplication. Say we have a matrix like this, 2 by 3 matrix, and we have another matrix, 3 by 2 matrix, and we would like to multiply these two, right? What we want to know is how many multiplications are involved. Multiplications are involved in this process of performing a dot product. So to obtain the first output cell, we have to multiply the first row of our first matrix with the first column of the second matrix. So we multiply 1 times 7, 2 times 9, and 3 times 11, right? So we have three multiplications here. That is, three multiplications were able to yield the first result, 58. Now, similarly, we will do another three multiplications here, another three multiplications here, and another three multiplications to obtain the last number. So this three multiplications that we have is the common dimension of the two matrix. So we have three multiplications times the first, that is the number of rows of the first metric, times 2, which is the dimension of this metric, and then times 2, this is the number of columns of the second metric, times 2. So this is the number of columns that we have. In other words, when we multiply a matrix of, let's say, dimension A times B and another matrix of dimension B times C, then the total number of scalar multiplications that we have to do to obtain our final product matrix is A times B times C. So A times B times C is the total number of multiplications that we have to do. So with that background, let's discuss the matrix chain multiplication. In AI and in data science and for solving many algorithm and mathematical problems, we often have to multiply matrices. As an example, say for example, we have a matrix of dimension 10 by 100, which let's say we call this matrix A1. Say we have another matrix A2 of dimensions 100 by 5, and another matrix A3 of dimensions 5 by 50. So obviously, if we want to multiply these three matrices, let's say A1 with A2 with A3, we can do so because the second dimension of this first metric is compatible with the first dimension of the second matrix, and its second dimension is same as the first dimension of the third matrix, and so on. So we also know that matrix multiplication is associative. What that means is I can either multiply A1 and A2 first and then multiply the product that we get, let's say A dash with A3, or I can also multiply A2 and A3 first and then let's say get A double dash, and then I multiply A1 with A double dash and I still get the same results. Now the question is, which one should we do? Should I do this or should I do this? Now when I ask which one, the question is in terms of speed, which is faster. Is A1 times A2 doing this and then doing A3 faster, or doing A2 times A3 and then later multiplying A1 to that product is faster? So now let's see the number of multiplications involved when you do this, the first choice. If we multiply A1 with A2, A1 with A2, the total number of scalar multiplications between the first two matrices is 10 times 100 times 5. So 10 times 100 times 5 is the number of scalar multiplications we have. Now, once we multiply this, the matrix that comes out will be of dimensions 10 by 5. Now, we have to multiply this matrix 10 by 5, which let's say we call it A dash, with this matrix of dimensions 5 by 50. So then the total number of scalar multiplications here will be 10 by 5 times 50. So this gives us around 7,500 scalar multiplications. Similarly, if we do A2 times A3 first, we see that multiplying these two, A2 times A3, we will need 100 times 5 times 50 multiplication. So 100 times 5 times 50 is the time required to give us a double dash, right? Now with a double dash, the dimension of our matrix here is 100 by 50. And now if we want to multiply a matrix of size 10 by 100 with another matrix of size 100 by 50, the number of multiplications we have to do is 10 by 100 by 50. So this gives us 75,000 scalar multiplications, which is way more. Similarly, if I have four matrices, A1, A2, A3, and A4, then we will have so many ways in which we could do the multiplication. I could either multiply A3 and A4 first, and then multiply with A2 and then with A1, and do perform all other possible kinds of combinations. Now, looking at these possible solutions, you can clearly see that so many of these solutions have common sub-problems. For example, the time needed to multiply A3 times A4 needs to be calculated for this solution and for this solution as well. So since there is a lot of common sub-problems among many of the possible solutions, dynamic programming can also be applied to obtain what is the best possible sequence of actions that we would need to take in order to come up with the minimum number of scalar multiplications. More specifically, with dynamic programming, what we would like to obtain is where to put these parentheses. Where should we put these parentheses in our multiplication chain so that we get the minimum number of scalar multiplications?